1 minute to the next presentation, so the speaker could share the screen with the presentation.
Is my presentation available?
Okay. I think you can put to full screen. Oh, perfect. Okay.
Okay.
Okay. We have 1 minute, but so I can start introducing you. So, okay, we have the second presentation of this session. The title is Comparative Analysis of ROS-based centralized methods for conducting collaborative molecular visual SLAM using a pair of UAV.
Yes.
The authors are Bulat Abbyasov, Roman Lavrenov, Aufora Zakiev, Tatiana Tsoi, and Evgeni Magid, and will be presented by Bulat Abbyasov. Please.
Yes. Thank you. Thank you. Hello, everyone. My name is Bulat Abbyasov. I am a master student of Kazan Federal University. In this work, I present a comparative analysis of ROS-based centralized methods for conducting collaborative monocular visual SLAM using a pair of UAVs. This presentation is structured as follows. I will start from a brief introduction of Kazan Federal University and our laboratory. Next, I will describe the problem considered in this work and our motivation. After that, I will present existing solutions of the problem, their drawbacks and limitations. Then I will present the experimental results of comparison. Finally, I will summarize the results. Kazan Federal University is the third oldest Russian university. Today, Kazan Federal University is one of the top 10 Russian universities with over 46,000 students and almost 10,000 employees. Our Laboratory of Intelligent Robotic Systems is one of the most international and successful labs of the university. The lab has a wide range of interests, and just within 4 years of its existence, we published our 100 research papers in English and Russian and obtained 4 intellectual properties. We are currently running about 15 different research projects with federal, local government, and internationally supported projects. Intelligent unmanned aerial vehicles nowadays play a significant role in, for example, security monitoring, remote area surveillance, and small package delivery. The drone can perform tasks autonomously or be remotely controlled using teleoperation. To reduce exploration time and exclude mission freezes in case of single robot failure, a swarm of drones is used. A swarm is a set of aerial robots where drones work together to achieve a specific goal. Usually, UAVs are applied for observation and underlying terrain exploration, for example, in military and civilian areas in research and rescue operations. In many serious and practical applications, a drone is required to perform a navigation task within the environment where GPS signals are available, for example, inside destroyed buildings. In such cases, other sensors are required. Vision sensors can be a good solution to the navigation without GPS in terms of the weight, cost, and information it can provide. There are many visual sensors, but monocular cameras are usually used due to reasonable price, lightweight, and ability to provide rich data about an underlying terrain. Vision-based monocular SLAM is one of the most interesting and challenge for robotics community research. Its goal is an unknown environment and localize a robot within this map. The main benefit of visual SLAM usage is that the approach doesn't depend on environments and can work in GPS-denied areas. Moreover, a monocular camera is a cheap sensor, but it provides the ability to reconstruct an observable part of a map into a human-readable 3D map. The research focus of SLAM systems shifts towards large-scale mapping, optimized path coverage, and large areas exploration. Using multiple agents in such scenarios reduces the required mapping time and adds a fault tolerance in case of agent failure. We selected two most popular feature-based centralized collaborative monocular visual SLAM methods with an open source implementation. CCM-SLAM are based on the original ROS-SLAM2 algorithm and extend it for multiple camera use. ROS-SLAM2 selection is due to its ability to detect loops and localize the camera in real time accurately. CORB-SLAM is an extended version of ROS-SLAM2. The system consisting of multiple extended ROS-SLAM2 instances the server receives host local maps and then creates a single integrated map. In CCM-SLAM, each agent runs only visual odometry with a limited number of keyframes. Data including detected features, weight descriptors, and 3D positions are constantly sent to a server. The server constructs local maps from whose keyframes, trying to close a loop and merge the local maps. After that, agents constantly download updated keyframes from the server. We used the Hector Quadrat integrated into the robot operating system framework for its modeling and control in the Gazebo simulator. The Hector Quadratl package provides a 3D model of the UAV, the right picture, onboard cameras, and plugins for control. For visual SLAM performance evaluation, we constructed a virtual Gazebo world shown in the left picture that contains the modified collapsed polystation model, which was extended with additional objects, including pieces of walls, terraces, and furniture. All vision-based SLAM calculations, both on the server and the client sides, were carried out on the same personal computer. The surface coverage goal is to find the optimal movement configuration of the robot equipped with sensors in order to maximize the visibility of a given three-dimensional large-scale region of interest. The aerial coverage path planning is a path planning where a UAV with a sensor, in our case it's a monocular camera, covers all accessible parts of an operation area. In our virtual experiments, two UAVs use three different coverage paths in order to explore the entire underlying area. A process of a surface reconstruction is a restoration of a digital representation of a scanned physical form. Scanning provides a 3D point cloud as a result of monocular visual SLAM algorithm execution. The two UAVs explore the collapsed building area within Gazebo virtual experiments and obtain 3D point clouds while running CCM-SLAM and CORB-SLAM algorithm. In the demo video, two drones are flying the underlying terrain exploring collapsed building. Current video frames demonstrate the CCM-SLAM execution. The green and white line is UAV's trajectories. Now CORB-SLAM is executing. Blue and green movable frames are monocular onboard cameras. We compared the two visual SLAM methods by considering the localization accuracy and quality of resulting 3D point cloud. Error estimation was calculated with regard to ground truth data, while two drones explored the underlying terrain using one of the three predefined trajectories. We used absolute trajectory error for measuring difference between points of the ground truth and the estimated by each SLAM algorithm. To represent the ATA evaluation function, we used maximum and minimum ATA values, root mean square error, median, and standard deviations. Experiments showed that the CCM-SLAM odometry localized more accurately at a vertical distance along the z-axis from a surface of an object while the CORB-SLAM odometry attempt to optimize keyframes by merging similar frames, losing a significant amount of valuable intermediate data. For example, in the figures above, you can see that a series of frames from minus 0.8 to minus 10 along y-axis and minus 12 to minus 10 along x-axis were lost. In such cases, the CORB-SLAM demonstrated the significant deviations from the of algorithms constructed sparse point cloud at the same high quality. This paper demonstrated presented a comparison of rhythm-based monocular SLAM methods, SLAM and CCM-SLAM. CORB-SLAM had a higher localization accuracy at a small scale local patch. At a global scale, CCM-SLAM demonstrated stable behavior with regard to a ground truth trajectory due to its keyframes optimization approach. That's all. Thank you for your attention.
Thank you very much for your presentation. So we have some time for some question, if any, from the audience. So I ask the audience if are there any question regarding this paper?
Excuse me, I have one question.
Yes.
Yes,
so
please.
Do you have any number of the compute for both algorithm, how much compute they are taking?
What?
Could you repeat, please?
Could you repeat, please? Yes.
Do you have any number that how much compute time they are taking?
Oh, okay. It's about the computing time needed for this algorithm.
We don't measure this time.
Okay. Another question is like, if I have to send this data to server, how much data I have to send to the server, and how much bandwidth of the communication is required? Any idea?
Please repeat.
The bandwidth required for the communication to the server. How many data you need to transmit to the server?
Each algorithm has own communication approach. For example, CCM-SLAM has own perfect transmission algorithm, and its goal to operate with real-time drones. And if you have to operate with real-time drones, you need to choose CCM-SLAM, because CORB-SLAM is don't have a perfect communication module.
Okay.
Okay.
And this module has been implemented on ROS or ROS2?
Yes. CCM-SLAM is.
No, I'm asking is ROS1 or ROS2?
ROS1.
Okay. Thank you.
Okay, thank you very much. Are there any other question? Oh, okay, I have a small question. You show the result in simulation in Gazebo. What
Yes.
about the implementation? You need, I think, very good hardware for the computational requirement. Could you give us an idea about how to implement in hardware these algorithms?
For real-time devices?
Yes.
It's our future plans to operate with real-time drones, but now we conduct it in virtual simulation.
Okay, but are there very high level hardware required for this implementation? Because you have a lot of computation to be performed, and the drone have limited space and energy. So have you any idea about what kind of hardware you could use?
I don't know.
Okay.
I don't know. But for real-time devices, CCM-SLAM is optimized.
Oh, okay.
In cases, in some cases.
Okay. Thank you. Very good. Are there any other questions from the audience?